Today we're going to look at the principle of moments. The principle of moments says that for a system to be in equilibrium, the sum, i.e. the total clockwise moments, must equal the sum, the total anti-clockwise moments, at any point in that system. If we consider this seesaw and apply the principle of moments, so we've got a man of weight 600 newtons who has a perpendicular distance of 1.0 meters from the pivot point where the log is in contact with the plank. And we've got a girl of 400 newtons who has a perpendicular distance of 1.5 meters from the pivot point. Relative to the pivot point, the man has a clockwise moment, and relative to the pivot point, the girl has an anti-clockwise moment. To work out the clockwise moment, we times the force, the weight of the man, by its perpendicular distance from the pivot. So we times the 600 with the 1.0 meters to get 600 Newton meters. To get the anti-clockwise moment, we times the force, the weight of the girl, times it with her perpendicular distance of 1.5 meters from the pivot. And that gives us, again, 600 Newton meters. So what we can say is our clockwise moment equals our anti-clockwise moment. So this seesaw is in equilibrium. I'm now going to apply principle of moments to an arm that is holding a weight, a load of 80 newtons, and the arm's been kept horizontal and it's in equilibrium. So let's look at the three forces that we need to take into account. So we've got the weight of the load, which is 80 newtons, and a distance of 35 meters from the pivot point, which is the elbow. What's got the weight of the arm, which is 20 newtons and has a perpendicular distance of 15 centimeters from the pivot point. And with the final force is the force along the bicep muscle, which we're labelling P, and that has a perpendicular distance of 6.0 centimeters from the pivot point. So before we can apply the principle of moments, we need to identify which are clockwise moments and which are anti-clockwise moments. So if we first look at the weight of the arm, you can see relative to the pivot, the weight of the arm is going to produce a clockwise moment. If we now consider the weight of the load, the 80 newtons, again, relative to the pivot, the 80 newtons is going to provide a clockwise moment. And then finally, force P, force along the biceps, relative to the pivot, it's going to produce an anti-clockwise moment. So we're going to have two clockwise moments and one anti-clockwise moment. So if we work out our clockwise moments first, so let's the first moment from the weight of the forearm, we times the weight by its perpendicular distance. We need this distance to be in SI units, so that would be 0.15 meters. So 20 times the perpendicular distance will give it moment. We then add the clockwise moment due to the 80 Newton force, and we times that weight with its perpendicular distance from the pivot, which in SI units will be 0.35. And so if we add these two moments together, that gives us 31 Newton meters. If we now consider force P, the anti-clockwise moment, so that will be P times its perpendicular distance from the pivot. So again, getting the distance in SI units, that will be 0.06, and then times by force P. And with the arm being in equilibrium, we can apply the principle of moments, where the sum of our clockwise moments will equal our anti-clockwise moment. So we can say our P times 0.06 equals 31 Newton meters. And then we can rearrange to make P the subject. So take the 31 and divide it by 0.06. And that gives us the force along the bicep muscle as 517 newtons. So there are two conditions for the equilibrium of a body. The first condition is that the resultant force must be zero. So remember, resultant is the overall force, or the net force must be zero. And from F equals ma, where F is the resultant force, this tells us then if the system is in equilibrium and there's no resultant force, then there's no accelerated motion. The second condition for equilibrium is the principle of moments, where the sum of all the moments about any point is zero, or to summarise, the resultant moment must be zero. And if the resultant moment is zero, there will be no rotational motion. So a system or a body that is in equilibrium will not accelerate and it will not rotate. And both these two conditions must apply. If we go back to the first example we looked at of the seesaw, where we saw that the clockwise moment equaled the anti-clockwise moment, so the resultant moment was zero. But for the system to be in equilibrium, the seesaw to be in equilibrium, the resultant force must be zero, or the net force must be zero. So we only had first the two forces of the weight acting downwards, so there must be a force acting upwards to balance the two weights. And this force is the normal reaction force acting on the plank from the log. And N, the normal reaction, must equal the combined weight, so equals 1000 newtons. And as before, we saw the net moment was zero, where our clockwise moment equals our anti-clockwise moment. So now this seesaw is fulfilling the two conditions needed for it to be in equilibrium. We're now going to look at another example to apply the principle of moments, and this is an exam question. And the first part of the exam question asks to draw and label the forces acting on the plank. So hopefully you will have identified four forces. First force being the weight of the student, which will be given by its mass times g, mg. The second force, the weight of the plank. And because it's a uniform plank, so assume a uniform density, we can take the centre of gravity of the plank at the centre. So that is 1 metre from end A. And to get its weight, it's mg, the mass of the plank, times 9.8. And the third force is the weight of the 5 kg mass. And the fourth force is the reaction force at point P, the pivot point, which is acting upwards. The second part of the question asked, how far is the 5 kg mass from end B? So I'm going to label that X. So we need to apply the principle of moment. So we say the sum of our clockwise moments equals the sum of our anti-clockwise moments. So before we actually start, let's consider which forces are going to produce a clockwise moment and which forces will produce an anti-clockwise moment. So if our pivot point is point P, R will produce no moment because its perpendicular distance from the pivot point is zero, so it produces no moment, so we don't need to consider R in this calculation. The weight of the plank relative to our pivot point is producing a clockwise moment. The weight of the 5 kg mass relative to the pivot point is producing a clockwise moment. And the weight of the student relative to the pivot point P is producing an anti-clockwise moment. So we've got 2 clockwise moments and 1 anti-clockwise moment. So let's find out the first clockwise moment due to the weight of the plank. So we take the weight and we times it by its perpendicular distance from point P. We know the weight of the plank is 1 metre from end A, and we know point P is half a metre from end A. So the perpendicular distance of the weight of the plank to point P is going to be the difference. So it's going to be the 1 metre minus the 0.50 metres. So its distance will be 0.50 metres. So it will be the weight times the 0.50 metres will give its clockwise moment. Now we'll consider the clockwise moment due to the 5 kg mass. So it's going to be its weight times its perpendicular distance, which I've labelled as y. So it's the weight times y, which we're adding on to the clockwise moment due to the weight of the plank. So these two are now going to equal the anti-clockwise moment due to the weight of the student. So to determine the anti-clockwise moment, we times the weight of the student with its perpendicular distance from the pivot point. We know the student is 0.30 metres from end A, and the pivot point is 0.50 metres from end A. So this perpendicular distance is the difference, so it's 0.20 metres. So it's the weight times the 0.20 metres. Now if we tidy up these terms, the first moment gives us 39.2, the second moment simplifies to 49y, and that anti-clockwise moment becomes 98. And if we rearrange to make y the subject, so we take the 39.2, move it to the other side of the equation, and then we divide by 49, we get y equals 1.2 metres. But remember, the question wasn't asking us to determine y, the question was asking us to determine the distance of 5 kg mass from end B. So we need to determine distance x. So we know the whole length of the plank is 2 metres. We know P is half a metre from A. We know the mass is distance y, 1.2 metres from P. And we know the 5 kg mass is a distance x from B. So x plus y plus the 0.50 metres must all equal the 2.0 metres. So to get x, we take our 2 metres and subtract the 0.50 metres, and we subtract y, and that gives us of x equals 0.30 metres.